All right, so we are going to look at importance sampling, which I kind of introduced on Wednesday, but we'll look at it a little bit more today. All right, and so you know, importance sampling is basically a form of Monte Carlo integration, and I think a better name for importance sampling would be weighted Monte Carlo integration, because it's not a sampling method. We've got we will look at sampling methods, and that's going to be next week. But for now, we're basically trying to perform Monte Carlo integration, but we're going to we're in a situation where we can't sample from basically our desired PDF. Okay, so in Monte Carlo integration, we say, well, what's the expected value of this function? What's the expected value of the function h applied to the random variable x if x has the PDF f? Okay, so the notation of this thing is, what's the expected value of x if we, what's the expected value of h if we apply h to the random variable x, and x is generated by a PDF f. Okay, and then that's equal to the integral over basically the support of x of h of x times f of x. And we can estimate this by generating a whole bunch of x values from f, right? So whatever function f you have, you generate a whole bunch of values x from it. You apply the function h, and you take the sample mean. And we saw a bunch of these examples, earlier this week on Wednesday, and on Monday we saw us doing Monte Carlo integration, right? But now we're going to face this question of what if we cannot generate values from this PDF, right? So f is a PDF. What if we cannot generate values from the PDF f? Okay, and so we basically have a couple options here. Okay, and one is that we'll learn how to generate values from any arbitrary PDF. Okay, and that's what we'll look at next week. Or we can perform importance sampling, right? So, so far everything we've done is that basically we've gotten to the point where your computers are so good that a lot of these techniques feel a little bit silly, okay? Because our computer, it used to be we could only generate values from the uniform distribution, and then we had to figure out ways to turn these uniform numbers into normal distribution numbers, or beta distribution, or gamma exponential, chi-squared, et cetera, et cetera, et cetera. Okay, but now our computers are great. R is a great language, and R can produce random values from basically any of these basic probability distributions, the normal, beta, gamma, exponential, chi-square distribution. R can produce random values here. So this has eliminated, like next week when we talk about generating random values, like it feels a tiny bit silly because R had, these built-in functions in R have kind of taken care of this stuff, right? It's a little bit like, you learned how to take the standard deviation by hand, but it also feels a tiny bit silly because R just calculates the standard deviation for you also. So, but anyway, that's what we're going to do next week. We're going to talk about how can we generate values from these different distributions, okay? But today we're going to focus on importance sampling, which is something that we can do if we're not able to sample from this distribution directly. Okay, if we're not able to sample from F directly, one option is to do importance sampling. Okay. All right. So what we're going to do is, we can't generate values from F. We're going to generate values from a different distribution. We're going to generate values from G, right? And G can be basically any PDF as long as it meets this one requirement. And this one requirement is that the support of F has to be contained entirely within the support of G. So either F and G have to have the same support, or the support of G has to be like a superset of the support of F. So whatever the support of F is, it has to be inside the support of G, okay? So we cannot have a situation where the PDF of G is equal to 0, but the PDF of F is greater than 0. Okay, that's not allowed. But other than that, if that condition is met, then any PDF of G will work out mathematically. Is the support the domain? Yeah, it's the support is basically where, well, it's technically a little bit different. So the domain of a function is basically the input range of X, okay? And the support of a PDF is basically where the PDF is greater than 0. Okay, so if we're talking about a PDF where the function is always positive, then basically the support is the same thing as the domain. But technically, if you have a function that like dips negative, then the support is just where the function is positive. So, but yeah, I mean, for PDFs, the support is pretty much the domain, okay, because PDFs are required to always be positive. Okay, and so so we're going to express this in this form over here. So we've got an expectation. We have the expectation of the function h applied to the random variable x, where x is generated by the PDF f. Okay, and this is equal to the integral of h of x times f of x dx. It's the integral of the function h, which is inside, multiplied by the density f. Okay, it's the it's the function multiplied by a density. Okay, the integral of that. And basically, I'm going to take that h times f, and I'm going to multiply it by g of x over g of x, which is pretty much 1. Okay, g of x over g of x is 1, so I'm allowed to do this. And so now I've got h of x times f of x divided by g of x times g of x. Okay, and I'm going to kind of gather this together over here. So I've got h of x times f of x over g of x times g of x. And if we look at this, okay, g of x is a density. And this over here is a function. It's a complicated function. It's h of x times f of x divided by g of x, but this is just a function. So the integral, the expectation of the function where x comes from this density f is, you know, the function times the density. And now I've got an integral in the same form of a complicated function times a density. Right? So here I've got the integral of a function times a density is equal to this expectation. Here I've got the integral of a complicated function times a density is going to be equal to this expectation. It's going to be the expectation of the complicated function h of x times f of x over g of x, where x is generated by the PDF or the density g. Okay, and we can do this as long as g of x is not 0. Okay, so as long as g of x is not 0, where f of x is greater than 0. Okay, so this will break if we're dividing by 0 when f is not 0. Okay, but as long as that doesn't happen, which is why the requirement is that the support of f has to be within the support of g, we'll be okay. All right. All right, is this okay? I guess the math behind here, where we're going to just say the expectation of this is basically the function times the density, and it's going to end up in this expectation. I hope that's all right. Okay, let me give you your first quiz answer. First quiz answer is B. B as in bear. B as in bear is your first quiz answer. All right, and so if we wanted to estimate using importance sampling, okay, well, if we want to estimate this value, the expectation of h of x, as if x came from f, but we can't generate from f, we're going to just generate values from x, okay? We're going to generate values from x, and we're going to, we just compute h of x times f of x divided by g of x. We compute that for all of the values of x that we did, and then we take basically the mean of that. Okay, so we're going to estimate this by just taking the mean of basically the sum, or not the sum, but the mean of h of x times f of x over g of x. All right, so if you pause and think about this, I think this is kind of a, to me, this is like a mind-blowing thing that we can do, okay? Because to me, it feels so crazy. So I'm going to do an example, a silly example, all right? So again, the idea is we are not generating values from F. We draw random values from G, okay? But we want to estimate the expected value of a function as if the values X that we drew came from the distribution F, okay? So we're drawing values from this distribution over here, but we want the answer as if they came from this distribution. Okay, so how is this going to work, right? Well, it works because whatever values we get from G, we are going to weight to them so that the result looks like, our sample, came from F, right? So here we're going to have F is a beta 2,4 distribution and G is a beta 5,3 distribution, okay? And this is a silly situation, but we're going to pretend that our computer can draw values from G, but not F. Okay, so we can draw values from a beta 5,3 distribution, but we're not able to draw values from a beta 2,4 distribution. Okay, or maybe we just have a sample from a beta 5,3 distribution. If we have a sample from a beta 5,3 distribution, can I still get the answer for as if the values came from a beta 2,4 distribution? Okay, and I need to distinguish between the idea of drawing random values and knowing the density, okay? So we will know the density function of beta, and we'll know the density function of this beta distribution, and we'll know the density function. It's just that the random sample I have comes from beta 5,3, okay? So I'm able to generate from G. I'm not able to generate samples from F, but I will know the density function of each of these things, okay? All right, so this is what F and G look like, okay? F, this is the blue distribution. That's F, that's the beta 2,4 distribution. And G is the red distribution, which is the beta 5,3, okay? And we're able to generate a sample from the red distribution, okay? So we are able to generate a sample from here in red, but we want the answer as if it came from the blue distribution. All right, so what do? Well, let's say we just want to do something simple, like estimate the mean. We want to estimate the mean of our of the distribution as if it came from the blue distribution, okay? So if you go the analytic route of the blue distribution is 0.333, and the mean of the blue distribution, the mean of F is 0.333, and the mean of G is 0.625, right? So if you look at the mean of the blue distribution, it's going to be, the mean is somewhere around 0.333, and the mean of this red distribution is, 0.625, right? If we didn't know the analytic answer, we could estimate it via Monte Carlo integration, right? And if we were able to generate from the blue distribution, it's easy. All you would do is you would just take your sample, you would just generate a whole bunch of values from F, the blue distribution, and then you would take the mean. Okay, and that's easy, right? You take your sample as if that came from the blue distribution, and you take the mean, right? But again, in this silly scenario, I'm not going to draw a sample from F. We're going to pretend like we can't draw the sample from the blue distribution, but we are able to draw it from the red distribution. Okay, so if I generate a big sample from the red distribution right here, R beta 5,3, and I take the mean, well, because it came from the red distribution, G, the mean is going to be very close to the mean of the red distribution. So when I take the mean of my sample, I get something like 0.625, right? And that makes sense because my X values came from the red distribution. So if I look at my red distribution, this is where X came from. X came from the wrong distribution. And so when I calculate the mean of X, I get 0.625, right? So can I use these X values, even though they are coming from this red distribution, can I use these X values to estimate the mean of the blue distribution? Does that even make sense to do that? Well, with importance sampling, the answer is yes, okay? And it seems so crazy because X is coming from the red distribution, and if I take the mean of X, I get 0.625, but I want to be able to use those exact same values and estimate the mean of the blue distribution, F, okay? And the way I'm going to do this is I'm going to take each observation and multiply it by an importance weight, okay? We're going to take each observation and we're going to multiply it by its importance weight. And what we do is we compare the blue and the red distributions, the F and G, okay? And so if you look at F and if you look at G, okay, what we see is that the red distribution, the one that we're generating from, produces way too many values like 0.7, okay? 0.7 is up here in the red distribution, and in the blue distribution, 0.7 is like way down here. So we're getting way too many values near 0.7, okay? And on the other hand, the blue distribution needs more values near 0.2, okay? The red distribution occasionally produces a value like 0.2, but very infrequently. So what we need to do is, like, anytime I see a 0.2, that needs to be valued a lot more, okay? We're not producing enough 0.2s, all right? So I'm going to take each of these things and I'm going to, whenever I get a value, I'm going to weigh them appropriately, right? So my sample comes from G, and when I look at my sample, anytime I see a value that's close to 0.7, I'm going to value those values. I'm going to weigh those values less, right? So if we look at the distribution of F and G, the density of G is much higher than the density of F, okay? And so the weight says, I've got to weigh those values less than 1, okay? G is bigger than F, right? G is in the denominator. G is bigger than F, so the weight's going to be less than 1, okay? On the other hand, when we look at our sample and we see a value near 0.2, we got to weigh those more heavily, right? So if you look at the thing, the red distribution very rarely generates a value near 0.2. And so when it does generate a value near 0.2, we got to make those values count, okay? So G is less than F, okay? F is greater than G, and so the weight is going to be greater than 1. Okay, is that all right? This idea of an importance weight, and it's just the ratio of the densities. And we're just saying, well, how often does this sample produce values like G? How often does this sample produce values like F? Or the sample that I'm sorry, not the sample, but the function that we want, F, how does that compare to the sample that we have, which is generated by G? And we look at the densities to kind of figure out the weights. And so the weights are calculated just using the density functions. So I'm going to take the density of the beta function with parameters 2, 4. This is my F. And I'm going to divide that by the density of my beta function with parameters 5, 3. Okay, so I do d beta 2, 4 divided by d beta 5, 3. And that's going to be my weights. Okay, so this is the d beta 2, 4, and this is d beta 5, 3. That's my weights. And now I take the same sample of values. I haven't regenerated the sample. This is the same sample of values that came from the 5, 3 distribution, the wrong distribution. I take those values and I multiply them by weights, and I ask for the mean, and I get 0.3328, right? Which is very close to the theoretic value of 0.3333, right? And I think this is impressive, right? Yeah, okay, so the question is, we have the PDF of F, we just don't know how to sample values from it, and that is correct, okay? So we do have the PDF, right? So we do have this function, the PDF of f. We just don't know how to generate values from it. Okay, and it seems a little strange. We haven't actually talked about generating random values, and that's what we're going to talk about next week. Next week we'll talk about generating random values, and again, it seems strange because on our computers we have all of these R beta functions, random functions. Okay, but here we're going to say we know the shape of the density, or we know the function of the density. We're just not able to generate random values. And so far, I've never asked you to generate a random value, which is actually a non-trivial task. And that's what we'll look at next week. Okay. Right now, we're just kind of using all of the built-in functions. So, and again, this is a bit of a contrived scenario. But I'm going to say we are able to generate from this beta distribution where the parameters are 5, 3. And we're just going to say, I've got this sample where that has been generated from this beta distribution with parameters 5, 3. Can I still use that sample to estimate the mean of a beta distribution with parameters 2, 4? And the answer is yes. Okay. All you have to do is you take your sample and you weight them accordingly, and you can get a good estimate of the mean of this beta distribution with these parameters. Okay, so the true value is 0.333, and we get something close to that. Okay, and just to kind of show that, you know, it's not a trick, this, if I create the histogram of X, it really is coming from this red distribution. It's coming from the wrong distribution, and all we're doing is we're just changing the weights on all of these things that we see, and we're going to get we end up getting the mean of the blue distribution, okay, which is F. So that's, I think it's neat, okay, that we can do this. So, you know, the idea of weighting these things kind of reflects, you know, you're basically highlighting the parts, you know, whatever parts in G that, you know, need to be emphasized, where, you know, we highlight those, and then any parts that G, you know, over generates, we kind of de-emphasize those with the weights. All right. So, all right. So we have a question: how do we determine a good G to use? So, you know, the answer is technically any G will work in the long run. It's going to work better if G looks a lot like F or H. Okay, so so the original kind of integral that we're trying to estimate is basically the integral of H times F. And if your G looks similar to F or your G looks similar to H, that's going to kind of give you your best performance. Okay. If F divided by G is close to 1, that will give you, you know, good performance. You know, your accuracy, if F and G are quite different from each other, okay, your accuracy can be expected to drop a bit. Okay, so, and you might need a bigger sample to compensate. Is that all right? So now we can kind of just rewrite our algorithm. The instructions are going to still just generate values X from G, a bunch of these X values from G, but we can say, let's compute the weights, and then now we just multiply the function that we want, and we multiply by the weight to get the value that we're interested in. All right, let me give you your second quiz answer. Next quiz answer is A as in apple. A as in apple. Second quiz answer. A as in apple. All right. Is this feeling okay? Sort of? Is it neat that I got this mean? I don't know. I think it is. Okay. Again, because we've got the wrong sample, but we're somehow able to do it. All right. So here's okay. All of these examples, again, I feel a little bit silly running these just because the computers have gotten so good that we can generate pretty much all of these distributions. All right. So we're going to look at, so one distribution we can talk about is the folded normal distribution, okay? And this would be what you would get is if you took your kind of standard normal distribution and you took the absolute values, okay? So your normal will generate positive and negative values, but what if you just took the absolute value of everything, okay? Well, basically you'll just get the positive half of the normal distribution, but it's going to have to be twice as tall because the whole thing still has to integrate to 1 in order for it to be a PDF. And now that we're only taking the positive half, I've got to make it twice as tall so that the total area equals 1. Okay, so so the PDF is going to, our f of x, the PDF is going to be 2 times the normal PDF. Okay, so I take my normal density function and I multiply it by 2. And when I do that, I'm going to get this. And all right, and what is the support of this? Okay, the support of f of x is going to go from 0 to infinity. So it's the, positive half of the number line. All right, and we might ask the question, what is the mean of this distribution? What's the mean of the distribution? Okay, so it's just the expected value of x, where x is generated by this PDFF. Okay, and so in this case, if you want to put it in the form of Monte Carlo integration, h of x is x. Okay, the function h of x is just x. So it's the integral of x times f of x dx. So that's the expected value, right? And f is this PDF. And so in this scenario, we're gonna use importance sampling to try to estimate this. Okay, but I guess before we do this, we can get kind of an estimate of the real answer. All right, so technically we don't need to use importance sampling because we are able to generate values from the folded normal. So here I just said, let's generate 1 million values from the normal distribution. So I'm going to do R norm and I get Z, and then I can just say, well, let's take the absolute value of Z and then what's the mean of all of these million positive normal values here. And I get something like 0.79738. Okay, but for now, we're going to pretend that we're not able to generate values from the normal distribution. Okay, so we're going to say, I can't generate values from the normal distribution. I can generate from some other distribution. Okay, but we're going to use importance sampling. All right, so we haven't talked about generating values, but we're going to say we're going to pretend we are able to generate values from the exponential distribution. Okay, so the exponential distribution, the PDF of the exponential distribution is lambda e to the negative lambda x, right? And here I'm going to just use lambda equal to 2. So I got 2e to the negative 2x. And we're going to say we are able to generate a sample from the exponential distribution. Okay, and the exponential distribution exists for values, from 0 to infinity. So the support of f, which is 0 to infinity for f, is identical to the support of g. All right, so we can use g in importance sampling because they have the same support. So that's fine. All right, and so we're going to generate values from the exponential distribution. All right, so the way this is going to work is we're going to use R exponential to generate a whole bunch of values. And for each of these values, we're going to compute the weights, which is going to be f divided by g. All right, so f is the PDF of the normal distribution multiplied by 2. Okay, so I just have d norm of x, okay, 2 times d norm. And again, we know the PDF, we're just not able to generate values from this thing, okay? Or maybe we are able to, but we're not going to use a sample from this. And then the PDF of the exponential distribution is this. It's going to be the exponential density. We plug in whatever xj value is, and we plug in rate equals 2. And then so the estimate of the function that we have, all right? In our case, h of x is x because we just want the mean. It's going to be h times the weights. Okay, so it's just going to be x multiplied by whatever weight this is. All right, so here's just kind of a slide with kind of just a little bit of code here. We're going to generate 1 million values from the exponential distribution using r exponential with rate equal to 2, right? And then the weights are going to be, we plug in our x values from the normal density, multiply that by 2, and we're going to divide by the exponential density, where rate is equal to 2. So that's going to be W. And then I take my x values and I multiply them by their weights, and I take the mean and I get 0.797. Okay, so the mean of this is 0.797. Okay, earlier we had generated, way back on this slide, we generated 1 million values from the normal distribution. Okay, and if I take the absolute value of that and I take the mean of that, this would just be the regular old Monte Carlo estimate where we were able to generate values from the normal distribution, and I get 0.79738. Okay, so a similar value. And then the theoretic value, which is what you would get if you solved it analytically, and I actually don't know kind of the substitutions that need to be used in order to pull this off, but the theoretic value will be the square root of 2 over pi, and this is the theoretic value. So we can see, our estimates come in pretty good. Okay, so we're getting pretty good estimates of what the mean should be. So we generated 1 million values and we're accurate to around 3 decimal places. Okay, 0.7976 versus 0.7974 versus 0.7979. Okay, so we're accurate to around 3 decimal places, which is what we can expect with about 1 million random values. So something on the order of square root of n is basically going to be your level of accuracy in general. Okay. All right. This is okay? Important sampling. All right, we're going to finish a little bit early today. I think that's all right. And so if we take a look at just kind of the different density curves, okay, the folded normal distribution. So in blue, I've got the norm density of the folded normal distribution in blue. Okay, the exponential density is in red, right? And this black line is the value of the weights. Okay, so we can see wherever red is above blue, okay, meaning the exponential distribution produces too many compared to the normal distribution, we have to weight those values to be less. Okay, so the exponential is, produces values near 0 too frequently, whereas the normal distribution should only produce it around this often. So we're going to weight those less than 1. Okay, and up until red crosses, so when red and blue are at the same height, the weight is equal to 1. Okay, wherever red is taller than blue, the weight is less than 1. And wherever red is lower than blue, the weight is higher than 1. Okay, and so over here around values like 1, the exponential distribution doesn't produce enough of these values, but the normal distribution produces more of them. So whenever we get a value like this from the exponential distribution, we have to weight them heavier. Okay, and it's just kind of interesting that the weight follows this curve like this. All right, so that's just kind of a I don't know, it's kind of neat that happens, but that's it. Okay, the last example I've got is we've got, maybe we want to estimate the value or the probability of ending up in an extreme tail, right? So we could say, what is the probability that z from a standard normal distribution is greater than 4.5, okay? And so we can get kind of the answer, and that would be p norm 1 minus p norm of 4.5, okay? or I could just do p norm of negative 4.5. And we get something on the like 3.397 times 10 to the negative 6. Okay, so this is, you know, about 3.4 in a million or 34 in 10 million or something like that, right? So if we wanted to do this via regular Monte Carlo integration, right? So we learned about how to do the normal CDF using Monte Carlo integration, kind of just using an indicator function. We can do that by just generating. So I already generated 1 million values from the normal distribution, right? So Z is, I've got 1 million values from the normal distribution. I can just say, well, how many of those are greater than 4.5? Okay. And so in 1 million values, I have a value, I got 2 values that were greater than 4.5. Okay. So my empirical estimate based on my sample of 1 million random normal values is, 2 in a million. Okay, 2 times 10 to the negative 6. All right. And this is not a very good estimate of this. Okay, so the true value is something around 3.4. And, I mean, really, with 1 million samples, I can really only expect either 2 or 3 or 4 or something. And we're not going to get like a super accurate estimate of this. Because this is a very rare event. The probability is on the order of 10 to the negative 6. And I'm asking, I generated 1 million values from the normal distribution, and it only happened twice. Okay, not a very good estimate. So I have a couple options, right? One option is I just, rather than generating 1 million, I decide to generate 100 million values from the normal distribution. Okay, so I can generate 100 million values from the normal distribution. It'll take a little bit longer to generate all of those values, but I can do that. And I can say how many of those came in greater than 4.5. Right? But rather than generating 100 million, I can also improve my accuracy by doing importance sampling. Okay, and so what? Instead, I can choose to use an exponential distribution that begins at 4.5. Let me draw you a little picture. Okay, so part of the issue here is that if you look at the normal distribution, it looks, it looks like this. And basically the tail, once you get way, we're basically going out to 4.5, and this tail probability is like super, super small, right? It's like, this is on the order of, 3.4 times 10 to the negative 6, okay? But, and we're asking for the expected value of, h of x, right? And in our case, our h of x is the indicator function that x is greater than 4.5. Okay, so this is my PDF f of x. And then h of x basically looks like this, right? 0 and 1, from 0 and then 4.5. Okay, and the problem is that my Monte Carlo estimate is that when I generate a whole bunch of values from f, when we generate from f, we get too many values that are less than 4.5. Okay, so most of the time, my h of x just equals 0. Okay, my indicator function is just going to be 0. All right, and so that's kind of the issue here. So what I'm going to do, I want to save this. I don't know if I want to save this slide. what I'm going to do is I'm going to generate from an exponential distribution, but I'm going to just kind of shift everything over to be to start at 4.5. Okay, so the exponential distribution the exponential distribution looks like this. Okay, so normally it starts at 0. Okay, what I'm going to do is I'm going to just shift this over. Okay, so here's 0, and then now I'm going to we get 4.5, right? So the PDF of this thing is lambda e to the negative lambda x, and we're just going to do lambda equal to 1. So my PDF is e to the negative x. Okay, and now I'm going to just shift this over. So basically, this is e to the negative x minus 4.5. Okay, or we can just say, well, you know what? This is the exponential distribution. So another way you can think of it is I got e to the negative x, but now, but we know that times some constant or divided by some constant, so that if I integrate from 4.5 to infinity, this thing has to equal 1. Okay, and if you solve for that, if you integrate from 4.5 to infinity of this thing, then you end up basically adding 4.5 to this. So you're going to get e to the negative x minus 4.5. All right, so this is going to be my exponential shifted over 4.5. All right, is that okay? So we know that this thing has to integrate to 1. This is the exponential divided by some constant, and the constant's going to be this. And so we just get e to the negative x minus 4.5. Okay, and so when you do that, the weights are going to be the normal PDF divided by our exponential distribution that's been shifted over 4.5. Okay, and then we just want the probability of being in the tail. Okay, we don't actually need to find the mean or anything like that. So the function h of x is x greater than 4.5, and that's going to be 1 for x greater than 4.5, or 0 whenever x is less than 4.5. Okay, and so here to generate my values, all right, I'm just going to generate values, 100,000 values from the from the exponential distribution, and then I'm going to just shift everything over by adding 4.5. Okay, so my x values are all have just been shifted over 4.5. Okay, and so I can plug these x values to get the normal density, which is what I have over here. So I'm going to say d norm of x, and then I'm going to divide by kind of the exponential function. So this is just, I can do e to the negative x minus 4.5, or I can just do d exponential of x minus 4.5. Okay, and this will give me my weights w. And then technically I should multiply w times h, but h is going to be 1. Okay, h is going to be 1 for all of these values because it's the indicator function and all of my values are greater than 4.5. Okay, so the probability of ending up in the tail is just going to be the mean of the weights times 1, or the weights times h, and I get 3.37, okay, which is a pretty good estimate of the true value, 3.397. Okay, so we get a much more accurate estimate based on 100,000 values rather than trying to generate like, 100 million values and just counting how often did I get a value greater than 4.5, because that's going to fluctuate quite a bit. Okay. And so this is what I get. Okay. All right, that's all I have for you guys today. This is last quiz answer. C as in cat. Last quiz answer for today is C as in cat. Okay. Any questions on this? We feel good? All right, I've posted the second homework assignment. That's available on week 3 in CCLE, and that will be due 1 week from Monday. So you've got about, like 10 days to work on that. Okay, so so that's going to be due a week from Monday, and that's your second homework assignment, and that it's going to cover importance sampling and all of the stuff that we've covered this week. Okay, that's it. Have a good weekend, you guys, and we'll see you guys later. I guess I also technically have office hours today, I think at 1, right? So I've got office hours later. All right, we'll see you guys. Okay, bye.